Whew. Okay, first of all, did everyone, I believe everyone took the test on Friday. They are graded, grades aren't in yet. They will be hopefully by the end of the month. Yeah. We're starting chapter 3 where we no longer need to use limit definition of derivative anymore. Yay! At least you don't. I will use it repeatedly to show you all the derivatives of patterns that we have, and by me proving them, it is motivation for you to just memorize them, because you don't have to memorize them. If you don't memorize them, though, you've got to reprove them. It's easier to just memorize them. So before you can say like that's a lot, go ahead, prove it instead. Like the amount of math that I know is very little. The amount of math that I can build is very much. So derivatives are slopes. And you don't have to write this down, you have it already. And this might blow everything up. Calculus the musical is real.
F of x plus h minus f of x all over h as h drops to 0 is the formula to find the derivative to otherwise state instantaneous rate.
F of x plus h minus f of x over h as h drops to 0 is the formula to find the derivative to find the slope. 1 point.
Infinitesimals dy over dx.
Why you wrote it out that way?
Like it just like it better that way. So f of x plus h minus f of x all over h as h drops to 0 is the formula to find the derivative.
We'll be coming with a rope. Newton from the limit of the slope.
I think it's over, but instant slope is not instant. In case you didn't remember, they're gonna sing it again.
Infinitesimals dy over dx. Why he wrote it out that way.
I just liked it better that way,
So
so
f of x plus h minus f of x all over h as h drops to 0 is the formula to find the derivative.
we'll be coming with a rope. Newton from the limit of the slope.
They just died. It's a painful thing I make you all go through. The person who taught BC with me before used to be a guy, and I would say that that was the two of us. Kids are like, aw. Anyway, so instant change, this is the general form, and it's the one that I'll be using to prove the rest of the patterns for you. This one was when A is a specific number. Again, you guys have got this already. The vocabulary for it, we could say, what's the instantaneous rate of change? Or what's the tangent line at this spot? Like, there's all these different ways to say this. Now, there's also lots of ways to write it. So, you need to know this. You don't need to know the words that are under it, but I will show them to you. They are all forms of saying, what's the derivative? And I almost never say y prime or write y prime because the science teacher claimed that it doesn't tell you change with respect to what. So in physics, when they got to angular velocity and the change of the angle over time, he was like, kids can't do it. They don't understand what's going on. So I tend to specify change in area with respect to radius, change in volume with respect to radius. I will name both variables like this second one. dy dx, or what's the change in y with respect to x, or the derivative of y with respect to x. It has the advantage that both variables are named. Here, we're changing with respect to radius. It matters. It's not a dy, it's not a dx, it's dA dr. And the other two could name the function, or actually plug the function in, like that's saying what is the derivative or the rate of change of sign with respect to x. Mostly I need you to understand the notation and not be surprised by it and know that it means do the derivative. Instead of writing down all of the words. So, let me do that. So you take it personal, please. Turn the page. Oh. So, I mean, each one has a point and a usefulness. When I was in high school, they had another one. Leibniz and Newton, they wrote things differently. One of them wrote dots over it to be first derivative. Whoa, that was cool. And Y double dot. Anyway, okay. This is just saying the domain of the derivative is either the same as the function or it might be a little smaller. That's all. If we say f prime exists, that means the function, the original function, had a slope or was differentiable at that spot. And if they say the function is differentiable, it means it works for all of the values in its domain. So again, the domain of the derivative is the domain of the function or a little bit smaller. And if we say that a function is differentiable, which largely the importance of that, a lot of the questions on the AP exam will say, this is a twice differentiable function, which means you can do the first and second derivative and they will exist for all of the values. And it's important that they tell you that. Right. And derivative is slope, right? So we can have slope on one side or the other, but not at the spot. So I can have a slope from the left side and I can have a slope from the right side, but the slope at A doesn't exist. That's all we need to know about one-sided derivatives. Okay? So I want to look at an actual picture and try this. Alex, what is the slope? We want to graph the derivatives or the slopes. What is the slope of the straight line from 0 to 1?
1.
Looking at the boxes, what's the slope?
Of the line.
It's up 2 over 1, so the slope is 2. Okay, so from 0 to 1, the slope is 2. What do I do at 0 and at 1? Should I put an open circle or a closed circle? Open. And the endpoints, it's kind of like questionable. AP will never, ever ask you at A and B. They will say something like the function is defined over AB and differentiable over round brackets A to B. They will not ask you about it because the math community complains and argues about what's appropriate and whether it should be enclosed or not, and AP has just said, never mind, we won't ask. Aiden, what about, Adrian, what about from 1 to 4?
It's 1/3.
1/3? Open or closed on the ends?
Closed at the beginning.
Closed at the beginning?
Open at the end.
Why would it be closed at 1? Like, is the slope right here, is the slope 2, which was the slope from the left side, or is the slope 1/3 from the right side? If you were traveling along this track on a car, and you were like gonna take off on a tangent, would your tangent take you this way, or would your tangent take you that way? Like, physics people, what's the answer, do you know? No? There is no slope, but like right at that corner, at that change, we're gonna say there is no slope at all. Can't do it. What? It's, ooh, that goes on my lines, oh well. It's like continuity, that the limit from the left and the right existed, but there's a discontinuity. There's a slope from the left, there's a slope from the right, but right there, if they're not equal, I don't have one. Lourdes, what's the slope from 4 to 6? Just a flat line like this. What's the slope? 8? 0? And Julia, the rest of the slope?
And
negative 1. So the graph of the slopes, the graph of the derivative of all those straight lines is all these horizontal lines. Linear equations have a constant rate of change. They have a constant slope. So this is what they look like. And at the changeovers, those are all open. Okay? Takes a minute for these to really work in. Questions? Constantine, can you see? Okay, again, derivative at a point, why? All right, so I might have lied a little bit. I want you guys to find the slope of this. If you know the derivative rules, you can use it. If you don't know the derivative rules, welcome to limit definition of derivative for one more time. So I got the slope at any point is 2x, which is that graph. So if I drew tangent lines on this, here it's a pretty sharp negative. Here it's still negative, but less negative. Here it's like negative 1. Right at the vertex, go figure, look at that. It's 0, it had a horizontal tangent line. As soon as I cross that and get to the other side, it's a little bit positive, a little bit more positive, a little bit more positive. Does it like, the hard part is that curvy thing created a straight thing. But what those things are, it's the relationship of the slopes. It doesn't make sense. Or at least feels slightly reasonable. And then, now that I've found this derivative, I can easily find the derivative at 50 is 100. Derivative at negative 7, negative 14. I can find all those things. Okay. What does this function look like? It's a
Absolute value.
There you go. It's absolute value. And this is how calculus will write absolute value all the time. And whether you know derivatives rules or not, what is the slope of y equals x? 1, because we know straight lines, algebra 1, the m, the slope attached to the letter, it's 1. And notice I did not keep the equals. I'm going to have to check that. Franco, on the other side, y equals negative x, what's the slope of that straight line?
Negative 1.
Negative 1. Okay, and then right at this corner, do I have a slope? No. So I'm going to leave these open. Cannot do a slope at a corner. Okay. We will see if this works. Every year, I'm afraid they're gonna take the thing down. Can you guys see those red lines? Sita, you can see them? Really? Okay. Because normally I draw over them, but doing the change in context is going to make the whole board shut down. These guys are the functions at the top. These guys are their derivatives. Who matches with who? There should be one that's kind of easy. Yeah.
Will the linear line match with the horizontal?
The linear line should match with the horizontal. Okay? Wow, it's changed. Stop. It says true. Yeah. Flare.
The other linear line is gonna match with the parabola.
This linear line is going to match with the parabola?
Yeah.
Why?
Because the slope is going to be like staying consistent. It's not gonna be a straight line, but it's gonna be.
The slope is a straight line.
Well, okay, not like a horizontal line.
Okay.
That's what
So, one key piece of information that I look for on this parabola, where was the slope 0? Right at that turning point. So is there a 0 in the function then? Yes. And as soon as we hit that 0, the slopes then became negative. And here the slopes become negative. And then beforehand the slopes were positive. So that looks good. What about the wiggles? Evan, do you see one?
Yeah, the fourth one with the x cubed graph is going to become the parabola.
So the x cubed graph is going to become the parabola. Why?
Calculate the first one power less.
Okay, because we know power rule, which we don't actually. We'll learn it tomorrow, officially learn it tomorrow. But while I don't know power rule, I'm going to look at -2. There was a 0 on this cubic, which a 0 slope. And on the parabola, there's a 0 there. And at 0, it looks like there's another horizontal tangent. And between these two, the slope was negative. Here, the slope is negative. Kind of works. Why doesn't it let me move them? Anyway, all right. So yeah, those worked. True, I agree. A new batch. George, do you see one? I mean, this is hard because the power rule thing doesn't work anymore because I got 2 parabolas for the cubics and 2 linears for the parabolas. Cameron thinks he sees one. Cameron, what do you think?
The parabola on the top and the
There's
second,
2 parabolas on the top.
The second.
This one.
The third one, sorry.
This one.
Third one. And the second line on the bottom.
And the second line on the bottom, why?
Because the vertex of the parabola is at kind of like close to 1/2, and that's where the slope is 0.
The horizontal tangent on the parabola matches up with the 0 for the straight line. Yes, I agree. Okay, so that makes another one pretty easy. What's the other parabolas? The other straight line. Okay, what about the squiggles? Kari?
The one on the top left would be the one on the bottom right, the slope is always positive.
Okay. Slope is always positive. Gets close to 0, but doesn't actually hit a 0. All right, so that means this guy has to go here. And again, I would match it up with the horizontal tangents. Oh, I don't want those. Okay. This one's fun. Mayan, do you see one? The two straight lines match. So the horizontal line has a slope of 0, Amelia?
The first one on the top and then the second one on the bottom.
First one on the top and the second on the bottom, why?
Because it changes at -1 and 2, and there's a 0 at -1 and 2.
What changes at -1 and
Like
2?
the slope.
The slope goes from negative to positive and positive to negative, okay? Yeah, Nathaniel.
The fourth graph to the third slope graph?
Because
Like the slope is 0 at -1 and 1.
the horizontal tangents on the original function hit the zeros of the parabola, which means this. What does this top function look like? Cosine. What does this bottom function look like? Try again. Negative sign. There's a thing. I will prove it 2 or 3 ways. It will be fun. But yes, the derivative of cosine is negative sign. All right. Sadie, do you see one?
The first one on the top and the first one on the bottom.
Why?
Because the slope is always, because it never goes negative.
Slope is always positive. So the derivative is always going to be above the y-axis, or x-axis, that is. Flynn, do you see one?
The third one on the top matches with the fourth one on the bottom.
Because the horizontal tangent is at 1, so that means this straight line matches that straight line. And again, the wiggles meet the wiggles. What's the slope on the top look like? Sine. What's the slope on the bottom look like? Cosine. Positive or negative?
Positive.
Positive. Yep. Okay, there's a particular shape I'm looking for, and it's not giving it to me. Ooh, the last one on the right. I mean, I think it's obvious because the fourth one, because there's no others like it. Those are the hard ones. If there's a bunch of this stuff on the top right, it's hard to pick out the one that matches the heartbeat look. Okay, so eventually you will be comfortable matching these up or possibly even drawing the derivative. This is your first exposure. Homework. Let you start on that. Wow, very early. The homework is day 9, which is page 103, 1 to 4, 7 to 10, 13, 14. I will try and get more of those up. There are textbooks behind Evan and Sita if you would like to get a book. So tonight's homework specifically is Yeah, rite of pass. Whoa, sorry.
Yeah, but you're struggling on that. You put it back, okay, go. What the hell?
scaring anybody.
You got a copy. I'm so scared.
It's my stomach.